Hello and welcome to day 17 of Advent of Code. We will again try to solve both puzzles using Kotlin. And yeah, I'm curious how hard today's problem will be. I definitely noticed that we have been hitting the 2-hour mark, I think, on at least the last couple of videos. And yeah, I'm considering cutting this into two parts, like for puzzle 1 and puzzle 2. Depending on if this increases in time, just to keep it watchable and not have like hour-long videos. Another option, maybe I will cut parts or fast forward parts just so that it's not too long. Yeah. But before we get into that, let's maybe just read the day 17 puzzle. Let's go. You finally decode the elf's message. Hi. The message says. You continue searching for the sleigh keys. Ahead of you is what appears to be a large ocean trench. Could the keys have fallen into it? You'd better send a probe to investigate. The probe launcher on your submarine can fire the probe with an integer velocity in the x forward and y upward or downward if negative directions. For example, an initial xy velocity like 0,10 would fire the probe straight up, while initial velocity like 10 - 1 would fire the probe forward at a slight downward angle. The probe's x and y position starts at 0, 0. Then it will follow some trajectory by moving in steps. On each step, these changes occur in the following order. The probe's x position increases by its x velocity. The probe's y position increases by its y velocity. Due to drag, the probe's x velocity changes by 1 towards the value 0. That is, it decreases by 1 if it's greater than 0. It increases by 1 if it is less than 0. Or does not change if it is already 0. Due to gravity, the probe's y velocity decreases by 1. For the probe to successfully make it into the trench, the probe must be on some trajectory that causes it to be within a target area after any step. The submarine's computer has already calculated this target area. Your puzzle input, for example, x from 20 to 30, y from -10 to -5. This target area means that you need to find initial x, y velocity values such that after any step the probe's x position is at least 20 and at most 30. And the probe's y position is at least -10 and at most -5. Given this target area, one initial velocity that causes the probe to be within the target area after any step is 7,2. So it's 7 into this direction and 2 up. And then I guess it's always -1 in this case on both. So it should be 1, 6, 0, 5, 4 -1, 3 -2, 2 -3, 1 -4. Then we'll just fall -5 and so on, but here it's already in this area. In this diagram, S is the probe's initial position, 0, 0, the x coordinate increases to the right and the y coordinate increases upward in the bottom right positions that are within the target area as shown as T. Yeah, we just looked at this. Another initial velocity that causes the probe to be within the target area after any step is 6, 3. Okay, here. Another one is 9, 0. Okay. One initial velocity that doesn't cause the probe to be within the target area after any step is 17 - 4. 17, 16. The probe appears to pass through the target area but is never within it after any step. Yeah, okay. jumps from here to here. Instead, it continues down and to the right. Only the first few steps are shown. If you're going to fire a highly scientific probe out of a super cool probe launcher, you might as well do it with style. How high can you make the probe go while still reaching the target area? In the above example, using an initial velocity of 6,9 is the best you can do, causing the probe to reach a maximum Y position of 45. Any higher initial Y velocity causes the probe to overshoot the target area entirely. Find the initial velocity that causes the probe to reach the highest Y position and still eventually be within the target area after any step. What is the highest Y position it reaches on this trajectory? Okay. This one is definitely a tricky one because I have no clue. So, what can we do if we have no clue? It is brute forcing. Which means we try everything until we found the thing we want to find. The problem is here is what do we brute force over? What are our inputs? Because it's not like we have a range already. It's not like we can go from x0 to x1000 and we just need to check all of them and then we are done. Here we can essentially, like the input we are looking for is the x and the y velocity, initial one, which is kind of this point here, right? And this point can be any point here, could be our start one. We could be this, which means x, although step over here, and then y 0. And it could be here and here. So in this two-dimensional space, but it's not confined in any way. Like we could also pick a y that is somewhere up here that is not even drawn. And in fact, what was the answer? 6,9. Okay, 6,9 is quite small. And the maximum y doesn't matter for our initial pick. So we need to somehow essentially define a two-dimensional space which is guaranteed to include, in the best case, all points that hit this area. It's fine if it's too large, because too large means just it takes more time. And maybe that is fine. We actually need to look at the actual puzzle. So it's an area of x 153 to 199 and then minus 114 to minus 75. Okay, I think that is more or less similar to this problem. It's still to the right and to the bottom. We do not need to like shoot backwards. That would be awkward. So we can assume we have an example like this. It will just be larger. That is fine. And for every, let's say if we have this point, we kind of simulate this. And either we end up inside the target area, then we can stop. We know this is a valid way to shoot our probe or launch our probe, and this was the highest one. The other thing is we need to somehow also stop if it doesn't hit like this. We do not want to continue forever. So I guess since we are only going to the right or down eventually, I guess as soon as we're below this area, we continue falling and we will never hit it, so we can stop if you're past this line. I think the same is true for here, the right side. Because if we still have velocity on the x-axis, that we moved past this point, there's no way to get back anymore, so we can already shoot or launch probes by following the velocity, and then once it hits, it hits. Once it's outside, it's outside. And then we only need to define what is the area in which we need to try all the things, and then we brute force our way through that. And then in part 2, we might fall onto our nose because the brute force doesn't work anymore. For the area, I think... So it needs to be at least 1. We need to move any step, right? And 1 is quite short. It will probably never hit, especially in this large example here. But we also know that on the right side, if you have an x velocity that on the first step is already past this thing, it won't hit. So we could at least limit it to 1 to furthest x of this area. This gives us nice area we can loop over. The problem is for every x, we need to test all the points above, and we need also a stop point. Like, if as an example we take 1, like if we shoot here, we won't hit. If we shoot here, we won't hit. If we shoot here, we won't hit. And if we continue this forever, we will never hit. So what is the point where we actually stop? Because if we are like at 1000, we will still drop below this line and never stop. So when is the point where we decide, okay, it's time to move on to this one? Maybe we could also try the opposite. We start here. And if we shoot up, let's say we start straight first, we will hit, and then we move 1 up, we might hit, and at some point we are so high How about, before we think about the range, we will write the code that actually simulates this. And to be honest, there's only one target area. At least now. I'm not sure what part 2 is, but for this one target area, we could also just, if it's fast enough, we could just create a huge room. Like, we know it's between x1 and 200. If it's fast to simulate, we could go up to 10,000 and just see. And if our minimum is somewhere below 10,000, then maybe it's fine. We could like brute force really, really hard. just needs to be fast enough. So let's write code to simulate this. We are day 17 and we need a file, day 17. We will have a part 1 and we will have a part 2, hopefully. And we will have a main function that executes part 1. And then we want to go and add a test. All right. So first thing to decide, as always, is how do we want to represent this data. We have an area. I mean, there's no need to somehow keep track of those points in like a 2D map or whatever. We only need to remember this area. And then the start is always 0, 0, I think, yeah. So if we have, so we only need a velocity and an area, and then we can simulate the probe launch, and then we return, does it hit? And I think it will be important. I'm not sure yet, but I still have hope we will figure it out. I think it will be important whether it will go out here or go out here. I think my gut feeling is that will help us to narrow down the scope we need to search in, but I'm not sure how yet. But I think it will be important. So we will return, does it hit, or is it misses it below, or misses it too far, kind of. And also how high it was. So let's do this. So we need an area, a target area, which is kind of this. It's an X range and a Y range. Maybe we want to actually represent this as a range. X range. How do I write a range? Int range. And this is essentially this. Okay, that works, nice. And we have a Y range of this. And then we can at least write the code that launches a probe, gives us those values, and then we can add some test codes. See, this should hit, and we should get the height, and then this should be 45. And once we have some code that brute forces, we can see if we can find the 45. Looking at those values, there's another interesting point. Like this is 0, 0, and going up goes up in Y. So usually, so far it was X and Y, and now it's X and Y is going up the x-axis instead of down, but that should not be too hard. Oh wait, I shouldn't write those values here because this is an area that can be anything. And then I guess we have something like launch probe, and this one needs a target. And then it gets a velocity, I guess. Initial velocity. x initial x velocity. Oh god, this is awkward. Let's create a class for this. And that is x int and a y int. Initial is a velocity. Right, and then we just need to return a result. Should this be... Yeah, we could turn this into a sealed interface result. And then either we have a hit. Do we need all the points along the way? It depends on whether we ever want to print this to the screen. Maybe we can skip that for now. We can still add it later on if we really want it. So the result will either be a hit. It's a hit. And the hit is a result and contains what? The max height. Does it need more? For now, not. We only care about, hey, this has hit. Or it's miss, maybe miss bottom and miss right. Miss bottom. Maybe it doesn't need any data for now. Or miss right. And then launch probe will return a result. So let's create a test case, and our first test case is exactly this case. This is our target area. Test velocity of 7.2. Our target is target area. Just steal this code as it is, I guess. Let's write it like this. This needs a test annotation. Now we say result launch probe with velocity 7.2 and this target, and then third true result is result hit. We think it's a hit, and then at some point we also want the height. Result as result hit, and then a third equals, this should be 1, 2, 3. 3, and this is our max height. We run this and it should fail. Okay, not implemented, that is true. Now we launch a probe. How do we do this? We need to keep track of where our probe is. So we have an X, which is exactly our initial one. So in this example, that will be here. And then we simulate. And then we need to check while it's not any of those. And maybe this is maybe this is something we ask the target area. Something like our result is null, and while result is null, we do something and then return result. And we could say we pass in this position into the target area, something like target determine result or get result or determine result of X and Y. This will return. We can't use those types, I guess, because this already needs a height. We need to keep track of the height as well. But we still want to ask the target area. So maybe need different kind of result. Or we make max height not part of it. And return this separately. So our result would be a hit. Yeah, let's see. Or the probe is still going, still traveling. How could we name this? Either we hit, either it's miss bottom, it's miss right, or it's ongoing. Can't think of anything better right now. So this will not return a result. Maybe, or maybe it will. The pair of the result and the height. And we need to rewrite our test. And this will be something like this, max height. And then we use this here. I don't really like those. The problem is I want to return a probe result here, and this is a target. I want to use this here as well. And I query the area. So yeah, well, maybe I create two. Yeah, let's go back. Damn. So a hit includes the max height as an int. Oh no, it's a data class. And this only returns a result now again. Oops. And for the other one, we create something specific. Area result, maybe. Which is either it's a hit, object hit area result, or it's ongoing, or it's one of those. And we need to translate between those. Not great, but maybe nicer than reusing the same type. Okay, so calculate result. So we have some kind of function on target area that we pass in an x and a y. And then we return a result. We don't need to implement this now, but we have target, calculate result for x and y. We do this once. Oh, sorry, we need an area result. We do this once, while, and now it's not null actually, while it's, oh, we could still return null, or should we return ongoing? Maybe ongoing is nicer. While it is ongoing, do something. And afterwards we say to result. We need to translate between both, kind of. And then at some point we need to pass in the max height as well. So maybe we keep track of that too. Var max height. We start at y. And we have a function that can translate. So it's target area, area result to result. Yeah, the types are not great. We pass in max height. Just the max height. And then we say when this is area result ongoing. This should never happen. Translating ongoing result, area result, is area result hit. Then we say this is a result hit with this max height, or it's an area result where it misses the bottom, or is an area result. Oh, no, it's right. And then we can return this. Okay, now let's implement the inner loop. So we haven't found any result in the first go. So we need to do essentially this again. We need to determine the new x and y, then see if our max height has changed, height, and then calculate a new area result. Easy. Who is going to do the simulation? we can do this on the velocity, I guess. Say simulate and then have a velocity and get a new velocity. And this essentially is described here. The x velocity changes by 1 towards the value 0. That is, it decreases by 1 if it's greater than 0. It increases by 1 if it's less than 0 or does not change. So this is super weird. Like, why would it ever be less than 0? Which means we shoot backwards, which at least here in this part 1 is never needed, and we will never try. But I guess we can still implement this. So new x, if x is larger than 0, it will be x minus 1, else if x is smaller 0, it will be x plus 1, else it will be 0. Stay at 0. Maybe we need this in part 2. Let's see. Then we have a new y, which is always just minus 1. And then return a new velocity. So we say, can we assign this like this? Oh, we actually do not keep track of a velocity. Oh, maybe we want to we pass it in as a velocity, but it's actually also a... Oh no, wait a second. We need two things. The current velocity and change the x and y accordingly. So we take our new velocity and say velocity simulate. Now we have the new distances, and then we say x plus x velocity and y plus y velocity. And then we say the area result is now to be recalculated for the new x and y. And the max height is the max of our current height and the new y. And this is do something. And we didn't implement this one yet. But this is what we are going to need now to run the test. Okay, so if y is smaller than, well, let's try to, so if y is smaller, no, yes, if y, this goes up, and then this is negative, and this is smaller than the range. Smaller than y range last. It's even smaller, yeah. Then it's, oops. Then we ran through the bottom. If x is larger than this, then we are past the right side. miswrite. Now we need to see, is it in it? X in X range and Y in X range. Then hey, we have a hit. And otherwise, still ongoing. We are still flying. Now we should be able to launch a probe if we actually use the new velocity. Wow, that would have been an awkward bug. Okay, let's run our test. Oh yeah, here we get a result again. Change this back. We need the hit object, result as result hit, and then we say result max height. Okay, can we? No. Hit max height. Now we should be able to shoot this thing. Oh. An insertion error. At least we got some kind of result. Where is the insertion error? What? Why is it not? Huh? Oh, here. What? It's not a hit. Okay. So what is it? What did this thing return? Miss bottom. Okay, which means we didn't do it correctly. No problem, no big deal. Let's look at the values. And then we do this for every round. And then let's run this again. Why is this red? Let's get rid of those. Let's run this. Okay. We start at 7.2. And then we are at 13.3. And then we are at 18.3. And then we are at 22.2. And 25.0. 27 minus 3. Minus 1, minus 2, minus 3. That looks correct. 27 minus 3. This should be the hit. 27 minus 3. And then 28 minus 7. 28 minus 7 should be in. This range is backwards. Minus 5 down to minus 10. That is a progression now. Wait a second. It's from minus 5. No, it's from minus 10 to minus 5. Why is this not in this range? Need a scratch file. So our range is minus 10 to minus 5. And then Print line 7 in range, -7 in range. -7 is in range. And 28 should be in this range, right? Oh. Yeah. Why is this not the case? The last. That is wrong. Does range give us... Oh, contains. That would be nice. Can we also get something like the min? No. Min off. Min. It's min or null now, right? And this is max or null. And then we can actually do x range contains x, and then y range contains y. Then it's a hit. Why it's still showing an error? It's just running it. Okay, now we get the right values. And we even get 3. Awesome, let's try this for some other ones. Let's look at those here. If we have a velocity of 6.3, that should look like this. 6.3, it should also be a hit, but it should be 1, 2, 3, 4, 5, 6. And then 9, 0. Nine, 0. 9, 0 will also be a hit. But now it will never be higher than 0. And finally, we will have 17 minus 4. 17 and minus 4. This one will get out of the right side. Oh, it makes me wonder, like, if this would have been here, then it would have been right and left. Maybe this case is interesting too. But that's something we need to decide later when we actually look at those. Here it's at least obvious this will be out on the right side first. And then we will not have a hit. And then we also try 6, 9. If we shoot at 6, 9, then there should be 45. Okay, we need to run all of them. Okay. They are all correct. Now we need to get rid of the debug statements for now. Now we need a way to find the max height. Let's say we have a function that does this. Find max probe height. So we get a target area. And we want a max height, and I assume we will always find one in those examples. So here we need to try things. Brute force our way. And then we will turn this. So if we throw this in as a test, find max height of example. We say if this our target was our max height, and we expect this to be 45. This is the thing we need to pass. Now, we need an X and a Y axis and define where we want to test from. As I mentioned before, the X axis is probably easy. In the worst case, we can do this. Everything that has a higher X than here will get past the area immediately. Everything that is into the left direction will go into the wrong direction. This one is too short. We could even skip over those until the point that kind of hits this one and then drops down. This is the shortest one, right? It needs to be one that hits this point in a motion that is always one step, shoots that high that it goes down in a straight diagonal line, right? And no, not in a diagonal, since the velocity changes, but it needs to be an X that gets one smaller, a velocity that gets one smaller. So it's this, where it's exactly here, it's 1, and then it can just drop the y-axis. So this will be a range which will be 6, 5, 4, 3, 2. 6 is now imagined, but 6, 5, 4, 3, 2, 1, and here it will be 0. So if we reverse this, it's 0, 1, 2, 3, 4, 5, 6. So I guess we need the number where the sum of those steps is exactly this length. So it's a similar problem that we had on one of the days. It's where we sum up natural numbers to be exactly this range. Like we had this example where we needed to sum up the range 1 to 10, and then we need 1 plus 2 plus 3 plus 4 plus 5 plus 6 and so on. And this is this formula from Gauss that we had before. So we could determine a smaller number than 1 if we need to, if the simulation is essentially running too long. Because if I look at this, simulating 1, maybe that is expensive to do, 1 and 2, because they will never ever be in this area. Essentially, we need to find a number where we sum up numbers in a row, like 1 plus 2 plus 3 and so on. That is the first one that is smaller than 153. So kind of reverse the formula from Gauss, or we determine it just by writing a loop. You only need to determine it once, which says we start by 1, add those numbers up until we have a number that is in this range. But for the first brute force attempt, you could say start at 1 to 199 in this example. We can't have, it needs to be in this area. Now the Y area is more complicated. We can also shoot down. So I guess our Y, what is the lowest Y? I mean, we can always hit this point, which will and we could hit this one as the lowest, but this one will be higher, so I guess our lowest Y is this one. So we already have like this area, kind of. Ignore these things on the right from here. Now we need to define how high can we go. And this will be hard to limit, harder. But we know that we need to come down until here. How can we find the highest one? For now, we could just pick something idiotic high. In this example, we know it is 9, pretty small. So we could write our brute force algorithm, pass in 20 for now, see if it finds it in a small one. Then we do this here with a ridiculous high and see if it's too slow. And if it's too slow, we try to narrow down the area we search in. So we will have a min-x. What's the minimum x? Need to move at least one step. Let's say this. And our max is, let's turn this into a range. It is at least 1, and it is at least the last one here. Needs to be in this range. This is a good thing. And the Y range is, it is at least, in this case we know it's lower, so we can cheat. Otherwise we would need to know, is it up here or low, but we know it's going to be lower, so we will cheat. You can also take notes like too large. on the left side. I think picking this as the further point makes sense, but we need to pick one that is here. I'm wondering, like, if we shoot to here, y needs to be 0 because it drops here. And then if it's here, I think we could recursively define an arc in which it needs to be. So let's continue. So y. We said y needs to be at least this one. Right? Yeah. So it's the max of the y range. The last, right? If we look at this, it should be -5, x and -5 here. 2, and this is now something we do not know. Max possible, no. Max possible height. This is something we need to at least make better. We said, let's try with 20, just for this example. And now we brute force our way. Our max height is... Oh, what is our max height? Probably... Maybe just take the min value. And then we just loop for x in x range, for y in y range. It doesn't matter which point we pick, we just need to pick all of them. Result, launch probe to this velocity x and y with the given target. If result is hit, no result hit, then max height is the max of max height and result max height. And then at the end, we return max height. And then let's also make a little check here. We shouldn't ever run into this, but just for debugging purposes. We will throw. Could not find max height. Now the problem is, in this example, it could be very, 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 very high. We could hit this in the actual case. But does this work here? It did work. We found 45. So I'm curious. In this example, let's pick a very high number and see. This was super fast to do. I don't feel like solving this for all problems. I want to solve it for this very specific problem. And then maybe in part 2, this will hit me into the face and it is not enough. But let's see. And I will not even try to parse this because it's only one line. Like, parsing this is not the problem. Like getting those values, like, yeah, skip those or skip those, read this range. Yeah, it is not hard to read this range, so I won't do it. I will skip over this, like we have done this so many times. We need to adapt this one, I guess. Do I want to pass this in here? Max possible height. Yeah, as long as we do not want to solve it more in a more smart way, we'll just pass it in. I'll keep 20 as default so that our test still passes. Find max probe height. This target. We say the max possible height is 1000. And if we get something close to that, then maybe we know something odd is happening. Simulate this. And it's running. It is running. Oh, the initial height is 1000. I was confused. Okay, this ran for a while. It's 6441. Let's say if we do it for 2000. Not sure how long this is going to run. Probably for a while. Let's see if this gets to a result. This is with 1000. Okay, our algorithm is horrible. It's still this number. So with that, I assume it won't get higher than that. So let's try this number. We're kind of cheating a bit, I feel like, because we didn't solve it in a generic way and a fast way for all possible things. But here's our first gold star. Let's try the second one. Oh no. Maybe a fancy trick shot isn't the best idea. After all, you only have one probe, so you had better not miss. Ooh. To get the best idea of what your options are for launching the probe, you need to find every initial velocity that causes the probe to eventually be within the target area after any step. You need to find every initial velocity that causes the probe to eventually be within the target area after any step. In the above example, there are 112 different initial velocity values that meet this criteria. How many distinct initial velocity values cause the probe to be within the target area after any step? Yeah. Let's see, maybe we can still try to force our way, brute force our way out of that. Let's maybe try that. What are the numbers? So for this one it's 112, and since we are already brute forcing, we can just count. And we just need to hope we found all of them. And we need... We only need the numbers, so we will just count them and not return them like we do here, I think. At least as long as we get the right number. Find number of hitting velocities. And if we use the same target area, now we go back here. And I think we will just turn this into something like find all probe velocities. Now we will again create a data class velocity results, and we will add a max height to it and a count, and then we will return this, and we will return this now with the max height, and now we also need to count. Whenever we have a hit, we count it. Whoops, count, then return it. And now third equals, first we need a result, find all velocity probes for this target. 112 should be the count. Now we need to fix this here. Result, right. Let's see if this still works. Let's run all the tests. Now our problem is that we search into not enough range. What happens if we say max possible height is 100? How many do we find now? Still not enough. If it's 200, not enough. We end up with 57. Why is this the case? So let's check our ranges we are looking in. We look from range x1 to x range last. Let's print those here quickly so that we see those. X in x range and y in y range. Before we further debug, let's make sure we look. So x should be in between 1 and 30. Oh, I know one problem. We said, since we are only looking for the max height so far, we have only been picking this, since this will always be higher than that. But now we need to pick the lowest one. So here we will say first. How many do we get now? 112. Awesome. With a height of 200. Now the big question is, first let's run all of them. Okay, and the big question is our 1500 really high enough or not? Because if it's not, then we might not find the right number. Let's say we want to run it for 2000. Should still be fast enough, I hope. Not. Oh. Let's wait a little bit. Actually, while this is running, in case this is not completing, we could. Oh, it's completed. We got 3 3,186. Oops, sorry. As like a kind of check, let's run this with 1000 and see whether it's more or less if we only run for 1000. It's still this number, so that makes me fairly confident that this is the actual result. Let's see. That's the right answer. We got our second gold star. Awesome. So let's take a quick look at our code again. Let's remove the debug statements while we are at it. The problem is our solution is okay-ish, and we can find the solution. What is a little bit awkward about how we do it is this max possible height that we pass in. So we should be smarter and find a height that makes sense, and I still think we can just calculate this. But still, it is fast enough if we pick a high number. So I'm happy with that and accept this as a result. Not the smartest one, not the best one. It's running quite fast and we could just limit the area we search in. But since this exercise didn't require us to do this, yeah, we are happy with that. I will upload my solution to GitHub, and there you can check out the solution. And if you found a way to make this faster and better, please let me know in the comments. And if you like this video, leave a thumbs up. Thank you. See you tomorrow. Bye bye.